Hello everyone, this is Chenyang Zhao in EE591 class. Today I'm going to present my class project, which is estimate and correct case-based trajectory errors using GIRF. As we all learned from this class, the gradient coils can be imperfect. This can be led by several factors, such as amplifier and coil characteristics, eddy current and vibration-induced fields. If we just assume the gradient waves are perfect, and we generate the case-based trajectory based on these perfect gradient waves, we cannot get reconstructed images with desired quality. Since actually our case-space data is acquired using the distorted trajectory, there is a mismatch between the acquired data and the trajectories used in reconstruction, and this mismatch leads to the image distortion. So this is the problem that I want to solve in this project. To solve this problem, there is a proposed method. That is, we can predict the distorted trajectory by convolving gradient waves with GIRF, which is gradient impulse response function. To get the distorted trajectories, we can match the distorted trajectories and acquire the data in reconstruction. We can improve the image quality. Here is the basic workflow that shows the idea of proposed method. Since in this project I used spiral trajectories, the gradient reconstruction was used for image reconstruction. The phantom that I used is the mink brain phantom, which is downloaded from BrainWeb. The resolution is 1 mm and 2256 pixels in each side. This is the phantom that I used. For reconstruction, I used a resolution of 2 mm. To generate the spiral trajectory and its gradient waves, I used a variable density spiral design toolbox. And here are some parameters that I used. The maximum slew rate is 150 Tesla per meter per second, and the maximum gradient amplitude is 4G per centimeter. The sampling rate is 0.004 millisecond, and the FOV is 28 centimeters. The case-space diameter is 5/1 centimeter. And in the experiments, I used the number of interleaves from 4 to 24. The corresponding readout time is increasing from 17 milliseconds to 3 milliseconds. On the right is an example of 16 interleave spiral trajectory. This is a single interleave. This is a whole sampling of k-space, and this is the gradient x and the gradient y. The GIRF data is downloaded from GitHub and it is measured by Zhao. The bandwidth of GIRF data is 35 kHz. I found there are some inaccuracy in the GIRF. First, the time integration of GIRF is not exactly 1, and it is not perfectly Hermitian symmetric, so I forced it to be real value in the time domain. This is the real part of GIRF, the imaginary part of GIRF, and the GIRF in the time domain. Here is an example of 16 interleave spiral sampling. This is GX and GIRF distorted GX. The red line is the GX, and the blue line is the GIRF distorted GX, the GY, and the one of 16 interleaves. As we can see, the trajectory changed a lot. After we obtain the trajectory, we can do the simulation of k-space data acquisition. Here I use the NUFFT. And I feed the trajectories and the images that we want to simulate. Then we will obtain the k-space data as the trajectories. I simulated two cases here. The one is the uncorrected reconstruction image, which uses the ideal trajectories to acquire case-based data. The other is the GIRF-corrected reconstruction image, which uses the GIRF-predicted distorted trajectories to acquire case-based data. The final step is to do the gradient image reconstruction on this ununiform sample case-based data. Initially, I have M1 knot of Kx and Ky now, which is uniformly sampled case space. The blurry and side lobes in image domain are introduced because of uniform sampling. Secondly, I use the Voronoi to calculate the density width and weighting the M1 knot, because for spiral, the sampling density is changing from the center to outer. There is a problem with Voronoi dense, which is that it cannot calculate the density width at most outer case space. I solved it by using a longer readout and truncate the data to the desired readout. Thirdly, I convolve the weighted M1 knot with a KB kernel, then apply Cartesian sampling on it, and finally, the de-apodization is applied to recover the image amplitude. This is just the ideal reconstructed images, which uses the ideal trajectories and data that are acquired from ideal trajectories. In the first line, the interleaves are set from 4 to 12, and the corresponding readout time is 17 milliseconds to 5.6 milliseconds. For second line, the interleaves are 14 to 22. Readout times are from 4.9 milliseconds to 3.1 milliseconds. Here is the uncorrected reconstructed images, which uses the ideal trajectories and data that are acquired from distorted trajectories, and I used the same interleaves and readout times as the last page. This is the GIRF-corrected reconstructed images, which uses the distorted trajectories and data that are acquired from distorted trajectories. This figure shows my expectation for this project. The errors are calculated using the mean square error between the uncorrected images or GIRF-corrected images and ideal images. I expected the error will increase along the increasing of readout time in both cases, but the GIRF-corrected one can maintain relatively good performance in longer readout. Therefore, this project can potentially work for high-performance, low-field MRI, since HPLF usually requires longer readout. This is the actual result that I got from experiment. The maximum readout was set to 60 milliseconds. In the figure on the left, blue line is uncorrected image error profile, red line is GIRF-corrected one. It matches my expected result. And on the right, I plotted the GIRF-corrected error profile individually. You can see that the error has the lowest value when readout is between 4 to 6 milliseconds. Okay, this is all about my project. Thanks for watching.